themes and use that. If it were me, I would do a Gantt chart. That's just how my brain works. Again, if you'd rather do burn down or burn up, that's your preference. I will grade them all identically, basically. So I just want you all to have a good feel for the rest of your project. And that's one of the points that you're presenting for your midterms as well. So it all kind of ties together. But again, if you have any questions, please feel free to let me know. I'll try to clarify things for you. All right, so we are done with project planning outside of your homework that you have to do. Now we're going to move on to UML proper. So this is something which is kind of contested in industry, I would say. Um, if you go to become a software engineer, like a industry software engineer where you write code more than do the requirement side of things, there's a 50-50 chance you never touch UML. Depends on your work environment. There's a chance that you use it every single day. It just kind of depends on again, your workplace and what their preferences are for how work is distributed, how we plan, how you model things. Whole lot of issues at play. But it's good for you to at least understand what it is, to get a feel for what the different types of diagrams are, kind of the purpose of all of them, and how they can really be a benefit to you. There is a lot of argument out there that UML is wasted effort from a business perspective, right? You already did use cases a while ago, right? So this is kind of the basics of UML, honestly. But there are a lot of feelings out there that doing this modeling activity, like you do it once and then it goes away forever, right? You're done with it. Or you get further down the chain in the software process and your requirements are updated. Well, crap, we have to also go back and update all of our models. That took us months just to hammer down our use cases, our class diagrams, everything. So not only do we have to fix requirements and code and all of our documentation with our customer, now here's also all of our artifacts, which we have to fix. And artifacts, I'm talking about like these models that we're going over here. But on the flip side, these models can be very powerful. They can very quickly show you issues in your design. They can be used at runtime if you go, a little bit experimental. So there's a lot of power in these diagrams. And is it extra effort? Absolutely. However, it can be very beneficial. And hopefully you can see how. But again, I'm just more so kind of preparing you. If this is something that you really like, you may get pushback. Or you may hate it. It just kind of depends. But it can be very, very useful, as I will say that. So what we're going to talk about today are basically a subset of UML diagrams. We're not going to go over all of them. There are a ton of models. We're going to cover the basics. So there's some structural diagrams, there's some behavioral diagrams. This should be UML 2.5. I forgot to update this one apparently. Basically, UML is a format. It's a formal standard for how to do modeling, and there are constant revisions to them. The current release is, I think, 2.5.1 of the UML spec. So I mean, that probably doesn't mean anything to you, right? Basically, all this means is that if a revision comes out down the line, you may need to update a diagram to fit the new standard or something like that. We have structural and we have behavioral, so static and dynamic aspects of it. Okay, so enough setting the stage. Modeling, again, you got a taste of with your use case diagrams, right? You get a feel for how you can communicate intent of your system. Maybe show somebody who is not technically oriented what your particular feature is doing. Or you can use it as a mental exercise to make sure that you're doing something right. I've got I should probably make this a separate browser window, otherwise I'm going to do this minimize and it's going to go tiny on me. Let me do this very quickly. So simple use case diagram, right? I took out my actors. This is kind of a starting point for some exercises today and probably next time. But this is my little roguelike game, right? I'm going to start a game and then I'm going to generate a level. Very, very quickly I can get the intent across to anybody about what some of the use cases I have to do, right? I need to program a start game module. I need to program a level generator. you can go crazy with use cases, and you're all, I'm sure, aware of that at this point, right? But again, the whole point is that we're getting the intent across and we're getting a feel for exactly what we have to talk about. So it's a simplification, right? Modeling is to basically take either something that is written in code, or maybe it's in your head, or it's written down in natural language in a requirements document, and simplify it. Again, the idea is communication and simplification of some task. You can also get system blueprints. And what this means is that you basically can, again, it's a level of abstraction, but you can basically delve into exactly what your implementation of your project has to be. And we're going to talk about things like class diagrams, which I think that you got in your intro to Java class if you've taken that. Well, you should have taken that if you're in here, I suppose. But you're getting the variables, right, and the methods and how various classes are connected to each other, right, what the interfaces are. These are going to be your blueprints. You can very easily give somebody else a class diagram and say, here, implement this. And then, you're off and running. You've saved a whole lot of effort just by giving them a model. And does it take effort to define them and refine them? Absolutely, but it can be very, very powerful. On the other side of things too, so structure and behavior, these are the two different types of models that I mentioned, right? So we basically have static and dynamic sides of the system. So structure, the organization, kind of more the implementation level, behavior, how things interact, how they communicate, how data is exchanged, basically how things kind of flow in your system. And there are a ton of submodels to describe each one of those points. But to this last point here in the slide, we're building models, again, for communication purposes and for understanding purposes. I can give each one of you a requirement specification with 500 requirements, right? And I can guarantee that each of you will implement it probably differently. It does not matter what your technical background is. It does not matter if you are all working on the same team. Everybody's going to have a different interpretation. But if you augment this with a model, I can kind of coerce you into how I would prefer it to be implemented, right? Because then you have, okay, well, class A has to talk to class B and it's inheriting features from class C. Oh, I never would have done it that way. Well, this is what you're supposed to be doing. And it's for understanding purposes and clarification in a way. All right, so with modeling, we get 4 aims. So you can visualize a system, right? So again, this is kind of everything that I'm talking about with simplifying and providing graphical models for communication. So we're visualizing. We can specify the structure. Let me just pop through all these because I've kind of already mentioned a lot of them. So visualization, specification, construction, documentation. 4 very important aspects to consider that you get with modeling. And again, okay, so let's say that we've communicated, things are simplified. We like what else can we do with this? Well, we can use it for auditing purposes later on, right? We can tie our models to our requirements, to our test cases, to our implementation. We can do that traceability exercise where everything is linked together. So there's a whole lot of things we can do here. And right now, I'm also assuming that you've probably have seen class diagrams before. We're going to talk about them and what they are, obviously, because that's the purpose of this lecture. You've done use cases because you all did the homework, right? So those are at least 2 models in UML that we've seen. Can any of you think of any models that are not software engineering related that maybe will help with any process? So this is kind of a high level question, right? There are other domains that use modeling, right? So we're using UML to model our software process. So what about architecture? What about construction? They don't use UML, right? Because that's not a software process for them. But do other domains use models? I guess is a simple question. I wonder if I do this, if this helps. Do other domains use models as well? I saw somebody who was giving tips on lecturing online to as well. Oops. As well. We can type today. If I ask the question in the chat, let me see if this helps too. All right, first blooper of the day. Perfect. Any thoughts on this one? Maybe either if the stream is slow or if we're all thinking about answers here. Let's go back to the construction point that I made. How do you build a building? What do you start from? Well, you start with meetings with clients and architects and project managers, right? So you get blueprints, sure. You get CAD diagrams, architecture diagrams. You could almost consider these to be, very specific models for their system. You're visualizing what it should look like. You're specifying dimensions and materials and things like that. Yeah, absolutely. Professionals have to have some sort of a plan. You as hobby programmers for fun, do you go by the seat of your pants and make the next best app out there? Well, yeah, sure you can. But once you're ready to take it to market, it's got to be polished. It has to be rigorously defined. And if you don't have like a plan, at least while you're working on it or before you begun, modeling can definitely get you there. And the follow-up question here, and architecture is one thing, right? You could specify this for any professional environment. Do you have to have a model that covers every single one of these points? Is that even possible? And the answer is no, it doesn't have to for each of these aims, which is why we have a whole range of different modeling types. And do you have to be an expert in every single submodel in UML? No. But if you can at least use the more common ones, get a feel for how they all work. And again, like I said, I'm not expecting you all to be UML experts. I think I've said this multiple times. If you want to use a formal tool that takes in like a class diagram and automatically generates code from it, which is possible, then yes, you need the syntax perfect, otherwise the tool breaks, right? Same for use cases that can generate class diagrams, or basically all of these tools can be fed in, or all these models can be fed into automated tools. And if this is something that interests you, I would highly recommend you check out some of the Eclipse plugins that are out there, because there's like Papyrus and Argo UML. Basically, there's a lot of like Eclipse-y type plugins which do auto generation of various things. There you have to have the syntax perfect, otherwise that tool breaks. But again, if we're communicating intent or visualization, as long as you can follow what the approximate standards are, you should be okay. So then, what is UML? We have all probably heard of it. If you're sitting in here for the past 15 minutes, you've definitely heard of it. So this is the unified modeling language. It is a language, meaning it has a formal syntax and semantics behind the scenes, running everything, for visualizing, specifying, constructing, and documenting. Documenting? I was going to say designing. Documenting a system. And specifically, we're looking at the artifacts here. Interestingly, UML started as 3 separate efforts. So there were 3 researchers out there. They called them the 3 amigos. Apparently, they argued a lot. I don't know these people personally, but these are big names in the software engineering academic community. So there's one guy called Grady Booch. He developed the Booch method. There's the object modeling technique by James Rumbaugh, and the object-oriented software engineering approach by Ivar Jacobson. So 3 people developing their own flavor of modeling a system. All right, so this often happens in academics where there is a clear need for something and a bunch of researchers will work on it, and everybody's going to have their own flavor of how this all shakes out. So what happened here was these three people in their research groups basically came up with their own techniques, and they did the smart thing, which this is a cynical, kind of jaded laugh that we should be doing a lot more in academics, the people who do research. They came together and they worked on it together. How crazy is that idea? And they came up with this UML specification. So uml.org is the website. Basically, there is a group associated with this now. It's a big deal, but it's these three guys. And they came up with this whole paradigm shifting technology. And this guy's picture is absolutely awesome now. He looks like he's gone full mad scientist, which is wonderful. But, and the reason why I kind of left and said this cynically is that there's some like techniques that I've worked on since I started doing academic research. And like there are so many variants of everything that I've done. They all do the exact same thing, but every research group has to have their own particular flavor and nobody works together. It's kind of annoying. I'm glad that these guys came together and worked together. But enough cynicism for you all. Everything is sunshine and roses in industry and in academia. All right, so what is this? So, okay, these three guys worked together. Awesome, great. They came up with their own, I think it's a nonprofit, but I'm not quite sure on that one. But basically, UML is this modeling language. It's process independent. So you could apply UML to any software design process, right? You could apply it to Agile, you could apply it to waterfall, to prototyping, doesn't matter. The intent behind the scenes is to model out your system, all right? So if you have a project where it's use case driven, all right, so you can kind of identify the use cases early on, like you all had to do for your projects, then it tends to work best, but that doesn't mean you can't apply it to something else where maybe you get a large swath of requirements at the outset. So use case driven, iterative, and incremental, meaning that we're going to refine things over time. It's not limited to modeling software. It's most useful when applying to software, but you could technically apply it to other engineering domains as well. You have a mechanical engineering project or maybe a senior design project where you have to work with electrical engineers or computer engineers or any other domain basically. Can you use UML? Sure. Technically, it will fit, right? The fact that you have use cases, pop back over here, right? So here's my use case diagram for my little gamey game. Let me copy and paste this. Let's open activate actuator. Let's use a Star Trekky term. Reroute power to shields, because that's what you have to do, clearly. Right, so this is a very pure electrical engineering process. Let's activate an actuator. Maybe I'm just turning on a switch and that actuates something. Or I'm shunting power down another set of wires, whatever it's going to be. Doesn't matter as long as it's something that we can specify, right? There's no code behind this. It's process independent. That's kind of one of the nice things here. So what are the building blocks of UML then? So let me pop these all up here. When I make these slides, I think, hey, animating them is going to be great, and then I don't know what I'm going to talk about next. So I always waffle year to year if I like animations or not. Sometimes they're good, sometimes they're bad. All right, so there are three key building blocks to UML. My kids watched Wreck-It Ralph recently, so you get Fix-It Felix just to lighten up the mood here. But the first thing in a UML model is a thing, okay? So this is going to be a first-class citizen in some model. And what first-class citizen means, this is a very software engineering-y term. Basically how active you are in this process. It's whatever is the focus of that model. Right, so if you have a class diagram, the first class citizen is the class. If you have a use case diagram, it's going to be your use cases and your actors, right? If we have a state machine, it's going to be the states. It's whatever the thing that you're modeling is. It's specific to that model type. So you have a thing, you have a relationship. This is how these things basically relate to each other. And what does a relationship mean? You all kind of got a feel for that a little bit already with those extends and includes and use case diagrams. If you did the class diagrams before, and I'm not assuming that you have, we're going to talk about them. Like if you have a generalization or you have a relationship or a composition, these are all relationships between artifacts. Does this class give another class its attributes and its methods because they're linked together, right? That's a relationship. How many of one object can be tied to another object? Like there's one professor and there's 30 students. That would be a relationship, right? For this class in particular, we specify the UML system, one professor and students, however many fits in this virtual classroom. All right, so we have these two, kind of the more important things. And then the diagram is going to be your graphical representation. So how do you draw this particular model? Use cases you've seen, we have a very specific way to draw them. Class diagrams, the same thing. You have a very specific way of showing things. And where the diagram kind of comes into play is it communicates the intent. Right? Use cases, we know what we're getting. Here are the use cases. Class diagrams, this is basically your implementation level. State machines, which I don't think we're going to be talking about unless we have extra time at the end of the semester, basically. Here's how your machine moves from state to state or configuration to configuration, or passing data in sequence diagrams. So basically, the thing to consider is that UML is abstracting out all that gunk of implementation and what domain you're in, and it just gives you a nice, clean model, which is honestly very nice from an engineering perspective. If everybody just learned UML, then we could all talk the same language, right? All right, if you have any questions so far, please feel free to pop in and let me know. We are currently at 2.5.1 in UML. You get two types. You get the structure and the behavioral diagrams. I mentioned this at the very outset, but structure is going to give you the static side of things. And when I say static, these are the things that are not changing. These are your methods and your attributes. These are your relationships between objects. Basically, you're getting pretty close to the implementation level with the structural diagram. The behavioral shows you how objects interact and communicate with each other. And they're called behavioral because they're the dynamic aspects of your system. It's the expressed behaviors, which is why they're called behavioral diagrams. Think of having two classes and they need to talk to each other. Well, what does talking to each other mean? Well, if you look at the structure diagram, it's calling functions, right, and passing data. But the behavioral diagram will show you at which point in time or which point in your flow this class will talk to this class, or which method is called to move you along your software flow. So dynamical, structural is basically the way to look at these things. So at a high level, here is the meta model of the UML specification. And if you don't remember what the term meta model is, it is a model to describe a model. If I remember right, you can go 4 to 5 layers deep with the modeling syntax craziness. So you can have a meta model to describe your meta model, and a meta model to describe that meta model. It's sometimes we go a little bit too off the rails with some of the research, but when you abstract out, you can do kind of cool things with the language. All this diagram is showing you is basically how all of the different types of UML diagrams relate to each other. Right, so here's your behavior, here's your structure categories. Under structure, there's your class diagram, but you can also have object diagrams, which we're going to talk about. You can split them up into packages to kind of lump things together. Deployment diagrams show you how to actually take your code and put it onto whatever hardware you're deploying it to, or how things interact when they're live. So structure is basically all of these types of diagrams. Behavioral diagrams, then, your activity diagrams, these are going to be the things that we're going to be talking about in a little bit. Actually, we're going to talk about the sequence and communications. But we're basically showing flow of information. We're showing timing. You know, we might be showing intent with like the use case diagrams. State machines, I would like to talk about these, but it's not super important for you all right now, so we're probably going to skip them. But basically, you get your dynamic aspects on this side, and then you get your structural, your static things on this side of the tree. Are we going to talk about every single one of these? No, unfortunately not. Which is a good thing. It can kind of make life a little bit easier for you if we just look at a subset of them. These are the more frequently used diagrams. Your class diagrams and object diagrams, these are going to be the structural ones we look at. Use cases we already looked at, fortunately, so we don't have to go through that again. But then we're going to talk about sequence and communication diagrams, and these are going to be the two under interactions. So it's important to know how things interact and how they talk to each other, basically. So this is what we are basically going to be covering today and Wednesday, depending on Friday, we'll see. First things first, so we need to start talking about the actual aspects of UML. We're going to start with the relationships because they're quite important. So relationships are connections, right? They're paths of communication between objects. In UML, they look like a path, which is a line between thing A to thing B, right? So the type of line, the type of arrow on the line, whether it's dashed or solid, this all matters for UML. So I would definitely pay attention to which lines mean which thing. But what do we get out of this? So we're going to talk about all of these points here momentarily, but we'll talk about dependency, so which thing relates to which other thing and how it takes information from there. We can abstract things out. We'll talk about all of these here. I'm going to be talking about these UML points in terms of a class diagram. So basically, our first little snippet of UML is going to be all about class diagrams. Keep in mind these relationships can apply to pretty much any UML diagram, though. So don't think you're limited to class diagrams for this one. Correct me if I'm wrong, you all have seen class diagrams in Intro to Java, I believe, right? Let me pop it in chat. Yes, 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 good. I was just about to check it. Okay, so we know that this is the class name, these are the attributes, and these are the methods. Okay, so the thing we care about with relationships here are these lines between classes, right? There's a whole lot of extra information being placed on these lines, right? We see different line types in here. For instance, this one has an arrow, this one does not. This all means something for us. And before we get too deep into this, there's one point to mention as well. Where does that use case diagram activity fit in here? And this is kind of one of the key things about UML that I really like is that typically one class or one diagram will inform another one. So it's basically like a domino effect type of thing. So you did the use cases, right? You have your verb noun syntax, right? So your, yeah, there we go. Start game, right? Verb noun, generate level, start game. The nouns might be your classes, the verbs might be your methods. So rough outline if it's your first time doing this, but I could easily make a class called game where one of the methods is start. Or I can make a class called level. One of its methods is generate. Makes a lot of sense when you think about it, right? Well, what do I have to do to start the game? Well, I need this attribute, this attribute, this attribute. I need, player name, I need background, I need hit points, whatever you're modeling. What about for level? Well, I need what level number it is. I need a 2D array for my 2D map or however you're representing your world. So you can kind of start thinking how you can kind of delve into how to actually fill out a class diagram, right? Is this the end all be all, right? You analyze use cases and you're done? No, you refine it over time, right? So we basically work through your use cases, all of your requirements, all your models, and you get your class diagram and you refine it over time. Okay, So we have our class diagrams. Ideally, we've kind of started to fill them in. Now we have to add relationships. So the first one we have is a dependency. So dependency is a dashed directed line. And what that means is we have a dash and we have an arrow. Consider this to be a uses type of relationship. So A uses B in some way here. Generally, it means one of these 4 points. B might be a local variable in A, B might be a return in A, B might be a parameter in A, or A uses some methods from B. You're not limited to one kind of type here, right? So we don't have any dashed lines in here, but like if this was a dashed line, enrollment to seminar, so this is a college class type of class diagram, maybe I need the seminar name to hook it up to the enrollment. So I'd be using this, right? But it'd be a dashed line. So that's a dependency. We also can generalize things. So this is where, if you are familiar with creating classes, you might have like a superclass, and then you have subclasses. Basically, the superclass is where you're constructing some kind of generic entity, and then you need to specialize various points out later on. And rather than having a lot of like redundant methods and a lot of redundant attributes, you have one superclass that has all of the common ones, and you specialize to subclasses. So kind of the common example with this is you have an animal as a class, and then you have a dog and a cat and an elephant and as your subclasses. Right, so we are specializing here. UML likes these kind of quotational relationship names. So this is a, so dog is a animal, elephant is a animal, student is a person, professor is a person, even though a lot of people don't think we are, we're just horrible lizard people. But, or vampires that sleep in coffins, but used to be human at one point. Again, we have a specialization type of thing. How do we model this? Solid line, open arrow. So basically you have this kind of triangle with a solid background here. Did we have generalization in here? No, we did not. But this is, and one of the other things I should mention too, I know I'm kind of like setting the stage, class diagrams, you probably all know this from Java. Can you do this in Python? Absolutely. I do superclasses and subclasses in Python all the time. Can you do it in C++? Absolutely. Can you do it in C? Yes, with extra steps. Point is, these design paradigms are pretty common across most programming languages. And if your language doesn't have classes, you can probably fudge it in there, right? You can make it work in such a way. So these diagrams are not only like process specific, they're language independent or process independent. They're also language independent. So we have generalization here. I've got an example in a couple slides with all of these on kind of one page as well, if you're a little bit lost. We also have associations here. So solid line with no direction. This is where you can start adding, like, I think they're called adornments, or that's where you add the little bits of text on the line. Right, like you can have multiplicity, like how many of A relates to B. Or you can have constraints or guards on here. You can have roles. So what is the role of A, right? If these are people, this could be professor on the line, this could be student, this could be TA, or I don't know, dean or department chair, right? It doesn't matter. Basically, we're getting information on the line here. This is assumed to be bidirectional. You add an arrow, then it becomes directional. So this is the multiplicity thing that I was kind of talking about. So this is where you add numbers on the line close to the class or close to whatever object we're modeling, right? So if we have a department, there can only be one department, there can only be one boss. Or for each department, there can only be one boss. For each employee, you can have 0 to any children. So this ... asterisk is important. Basically, this is your range that you would set up. and the asterisk is to any. So one boss can have at least one employee, or 20 employees, or 500 employees, right? So this is getting you a feeling when you start implementing things of how many different classes you would say instantiate per superclass, for instance, or, right? These don't necessarily have to be super and subclasses. So that's one of the things you can adorn on a association here. You can also add on, like I said, roles, or let me scroll back here a little bit. So here in this I don't want to say a class diagram, a course maybe class diagram, or a seminar, I guess. One student can be enrolled in any number, well, can have any number of enrollments in one seminar, right? So I am enrolled in here. And what does this tell you, like, to program? That's kind of a weird way to say it. If I'm implementing this class diagram, what does enrolled tell me? Like, I'm writing Java code, does enrolled exist? Probably not, right? It might be a Boolean somewhere, but this is one of those semantic things that is giving information to you, the reader, right? A professor instructs a seminar. That makes sense to me if I'm communicating with one of you what the intent of this system is, right? But does this tell me anything programmatically? Not really, but it's an adornment. It helps explain. However, we have a guard here. We have a constraint in curly braces. A seminar can have any number of students. In this line is specifying the waiting list, right? So if all of you have enrolled in the class, and then next semester, let's say you want to take another class, and it's already full, so you get on the waiting list. What does that mean? Well, any number of students can be on the waiting list, but this list is ordered in, first out. So here we have a constraint on this relationship. So to summarize, numbers are going to be your multiplicities. Raw text is going to be basically a descriptor for you. If it's in curly braces, it's going to be a constraint or a requirement for this interaction. You may also see square brackets. That's going to be a pure constraint where this has to happen, otherwise it doesn't exist, kind of a thing. Okay, so as long as that makes sense, please let me know. So these are our pure bidirectional associations, right? No arrows. We also can have a directional association, solid line with an arrow. You notice it looks like a normal arrow, not one of those triangle arrows. If we have an association like this is a has a relationship, or also a whole and a part relationship. So basically, example here would be B is a variable type in A. So let's say A is my game, B is my level, right? So this is class A, class B. My game might have an array of levels, right? So that would be game has levels, or animal has legs, for instance. So has a means it's basically including in the other one. All right, if we're good so far, let's get on to the trickier ones now. I'm probably overcomplicating this, but I'm just trying to get across that this syntax is quite important. Otherwise, if you start using the wrong line types or the wrong like arrow heads, it's going to mean different things if you read it. Right? If you talk to me, if you bring your model, you submit your homework to me and I read it and you use the wrong arrowhead, I'm going to assume that you're trying to use that particular arrowhead. Right? Like if you are giving me homework with a solid line and this type of arrow, I'm going to say, oh, it's a directional relationship, and that's how I will read your diagram. Whereas if you give it to me and it looks like this, well, now it's a dependency. And there's a slightly different meaning. And this is the syntax of the model. Okay. The types of lines have power and meaning. Okay, so aggregation and composition. Depending on your background, this might be the exact same thing. It might be something called syntactic sugar, just to be cute. Basically, one is logical and one is physical, if that helps. So with both of these, you're basically describing a bunch of parts putting together a whole. I don't know if example is going to track, but if any of you have ever done any like 3D modeling or CAD drawings in something like SolidWorks or AutoCAD, you make up a bunch of parts. It's like if you're building an engine, you need the pistons. Okay, so that's going to be a part. You need all the bolts that you model. That's going to be a part. The housing's going to be a part. So these are all going to be parts in your system. And then when you put the thing together as a whole engine, you put all the parts inside it. So you're composing all these parts in, or you're aggregating all of them in. Hopefully that example helps. But basically, you have a solid line with a diamond head. Aggregation is a white background. Composition is a black background. And what we have here to kind of distinguish them, aggregation is more logical, it's conceptual. What this means is that it's going to inform other diagrams like your sequence diagrams, how things are linked over time. I've got a good example here momentarily. Basically, there's a very strong relationship with composition. So let's talk about composition first. You create the composite and then you create the parts with composition. If you create an object, it can only ever be part of this one composition. You can't have multiples. And then let's say that you take, let's say that we're doing a software engine, right? So we've created a class for engine and all the parts these are all like classes. The engine is responsible for creating and destroying the parts, right? So if I'm creating a new engine class, that engine is responsible for creating all of its subparts. And when we're done with the engine, it's responsible for destroying all of its parts, right? So when you call like engine.destroy, that will first kill all of the internal parts and then itself. Whereas in aggregation, these are not strongly linked, right? Each part can instantiate itself or destroy itself. Very, very, very slight distinction when you're thinking about this mentally, but very important for, again, other tools or automation type activities. In general, the same type of concept though, and that's kind of why I'm spending a little more time here. It's a fine line. And the phrase I used was syntactic sugar because you're basically describing the same thing. It's just who is responsible for what is kind of the key difference here. So for some lovely, dad puns here, some examples. So generalization, this is your kind of. Aggregation is a part of. Composition is a part of. So a cardinal is a kind of bird. A truck is a kind of land vehicle. A land vehicle is a kind of vehicle. So this is a generalization. This is your solid line with the triangle at the end. Aggregation and composition, solid line with white diamond or black diamond. A wheel instance is a part of a vehicle instance. A door instance is a part of only one vehicle instance, right? Because this is the physically realized thing. This is the logically realized thing. Distinction makes sense, I hope. If you're thinking about this in terms of pure Java, think of who's responsible for creating and destroying the objects. That'll tell you if it's aggregation or composition. All right, couple more minutes here, so we'll wrap up some of the examples and then probably call it a day. So this is kind of blurry and off-kilter here, obviously a scan. But here we have composition, we have aggregation, we have a relationship. Let me do the one that's not highlighted. And we have no directional lines here. So a student is an aggregation towards the school, right? So we can have one or more schools, we can have any number of students. Is the school responsible for the student? No, the student is responsible for him or herself, right? So we are aggregating here. However, if we have a school can have any number of departments, right? Or at least one department. If I don't have a school, then I don't have departments. Kind of that fine line of distinction here. Now we have some kind of directional verbiage here on the line. So the member is pointing this way, attends point this way. This is kind of one of those extra information that you can add onto the line. So a student is a member of a school. A school has departments. An instructor is assigned to a department. You might have a chairperson who is also an instructor for a department. So this is kind of a high-level class diagram, right? We don't have attributes, we don't have methods. This would be one of your initial first takes at a diagram where we're basically just showing relationships. But just kind of one example for you there. And then we have another one. We have team. Basically, we're building an airplane. A team builds the airplane. Employees will be part of the team. Airplane is made up of components, which is made up of sub-assemblies. So again, you see composition here because components are being made up of actual entities. Airplanes are made up of actual components. Whereas an employee can be a part of a team, but we don't necessarily have the team destroy the employee if it goes away, right? The employee could be reassigned. Questions at all from today now that we're at the end of class? Anybody have any homework questions or midterm questions or anything like that going on? Just to give you a hot minute to ask anything that you want. If you do have any questions, don't forget Offstar start at 11 on Blackboard. I will be writing a Python randomizer to assign people to presentation dates. But everybody good otherwise? Hopefully. Just throw puppers in there. All right, well, if everybody is good, all good in the hood, I will see you all on Wednesday. Yeah, I'm trying to think if there's anything else I had to tell you all. It's basically just the homework and start getting good with UML. All right, bye everybody. I will see you next time and have a wonderful day. End stream.